what I'm going to do now is talk about a simple system. It's not a complex system. But there are some of these ideas about how to model and how to reduce and how to abstract systems that we're going to talk about. At the same time, I'm going to use some different mathematical tools that we'll be seeing again in the course. You shouldn't, maybe you won't be able to follow every single step, but you should follow most of the steps, and at least the types of math I'm using, you should have seen those before. If you haven't and you feel lost, at any point, please stop. But at the end, if you feel lost, especially, let us know, and like I said, we can have another separate session just on basic calculus, linear algebra, differential equations, whatever. But for the most part, for the rest of the class, we'll be, like next week, Oana is going to be talking about dynamical systems, which uses differential equations, and some of the important aspects of differential equations we'll probably review again. So don't worry too much. If it completely doesn't make sense, please let me know. Okay, so really simple system. Let's say you have a bunch of cells, like bacteria or something, and these are asexually reproducing. What does that mean? That means they just, I know they just make copies of themselves. So all the cells are identical, and what we're interested in is we're interested in understanding the total size of the population, how that changes in time, how that grows. So this would be relevant if you were, there's a lot of people on campus that do experiments with bacteria and yeast, and if you put, bacteria in a test tube or something, or yeast in a test tube and let them grow for a while, you'll see some sort of a growth curve. So let's see if these markers work. So let's say X is like the total population size versus T. You might see some sort of growth. Who knows what it looks like? I don't know. But you'll see something. And the idea is we're trying to understand this sort of macroscopic behavior, the behavior of the whole system, from the properties of the individual cells. That's the goal. Can you see if there's any other markers in like the conference room? Oh, there's probably not any there, right? But
no, here.
There's all these kind of okay, so the things we're assuming is that all cells are identical in all respects, and all cells will reproduce. Most of the cells will reproduce, and they'll die eventually. So one way we can represent this process is we can imagine we have one cell to begin with, and let's say that cell produces 3 offspring before it dies. And each of those cells produce 3 offspring before they die because they're all identical. So they're each going to produce the same number of offspring, at least for now in this very simplified model. And you get something like this. It sort of looks like the branches on a tree. So mathematically, we can, and this is like the first generation, this is the second generation, this is the first generation, this is the second generation, these guys, and then all these guys out here on the outside are the third generation. So what I would like to do is write down x of I plus 1. So this is going to be the number of total cells in the generation I plus 1. And I want to figure out how that's related to the number of cells at the previous generation. Okay, so let's just look at this real quick. So if I have 3 cells at generation I, in this case I have how many cells at generation I plus 1?
What's their death rate though? Like, how do you know the previous generation is not dead?
So what we're assuming here, I'm glad you brought that, what we're assuming is that the generations work like this. Everybody reproduces, and then, so let's say there's 3 cells here, we assume they all reproduce at the same time, and then you get the 9 cells, and then before the generation's up, these 3 die. So at the end of each generation, all the previous cells die, and all that's left are the offspring. So we can write this like this. We can say this is the sum down first, then we can talk about it. So Sj is the number of offspring the jth cell is going to reproduce. And then we're going to sum over all of the cells that are in the population at that time. And like I said, all of these are identical. So this is going to be the same for all of the cells, and we can just call it S. So if I sum that together, I'm just going to get xi times S. This sort of is a bit overkill for now, but you'll see why in a second. So all you get is this. You just get that the number of cells of the second generation are the number of cells of the first generation times some number. In this case, the number's 3. So you have 3 cells of the second generation, let's say. That means you get 3 times 3, which is 9 cells of the next generation. It's a very simple equation. So this is really the important equation, where S is number of offspring per cell, per generation. Okay. So this type of an equation here is like probably the simplest example I can imagine of something called a recursion relation. So it's just a recursively defined equation. And there are 2 aspects of it that are important. Sometimes it's called first of all, sometimes it's called a difference equation, an analogy to a differential equation. We'll see why in a second. But also notice here that time is discrete. So what I've done is I've broken up time, so this is time, into generations, generation 1, generation 2. And I'm assuming that I only can look at the system at these discrete times. One way of thinking about it is we're assuming that all of the cells just reproduce immediately, they don't take any time to reproduce, and then their parents die immediately, and then we move on to the next generation. Okay, so is everybody clear so far what's going on? Okay, so can anybody tell me what the solution of this is? So what if I want to figure out what xi is, not in terms of the previous time step, but just in general?
It's like S to the I.
Yeah, it's S to the I times x0. Okay, and the way I got that, most people will know how I got that, but the way you get that is you can just think about it like this. You just say, okay, well, in the 0th, let's say I start with x0. In the first generation, I'm going to have x0 times s, and then x0 times s squared in the second generation, and so on and so forth. So I get si times x0. Right? Okay, so this type of growth is typically called exponential. So it's some number exponential. So, looking at the solution, there's a couple things I want you guys to note. What happens if S, the number of offspring that each cell reproduces, is less than 1? What happens after a long time?
Tends to 0.
Yeah, it tends to 0. Does everybody see that? So this thing's just going to get smaller and smaller. As you square a number smaller than 1, it gets smaller and smaller and smaller, and eventually we get 0. Which makes sense. If the guys produce less than 1 offspring, it's not even clear what that means, but what it typically means is in an average sense it produces less than 1 offspring. So maybe this guy produces 1, this guy produces 1, and this guy doesn't produce any. You know, again, we're assuming they all do the same thing, so we're kind of getting into treacherous waters here. But then eventually, if all the guys aren't reproducing, eventually after some long period of time, you'll have 1 guy left, and then he won't reproduce, and then nobody will be left. What if S is bigger than 1?
It's infinity.
Yeah, it just grows without limit, right? It goes to infinity eventually. So this sort of branching process gets bigger and bigger and bigger, and more cells are there until, I don't know, they fill up the universe or something. So is that it? I mean, is that the answer? So we have this cell, these cells in a petri dish or something. We're going to put them in there, and they're just going to grow and eventually take over the lab and kill us all, right? That's what happens. No. So there's some limitation. What really happens? Yeah, there's a limited amount of resources. So in this, petri dish that these cells are in, there's some sugar, or some flow of sugar, and once you have enough cells in there, they're all not going to be able to get enough sugar, and some are going to stop reproducing, and the growth rate's going to slow down. So notice what I'm doing here. I started from a lower level, but I'm bringing some intuition about what should happen at the higher level into the model. This is the way models are really built. It's not this reductionistic bottom-up approach. Okay, so that's one limitation of the model, that it's basically assuming that you have unlimited resources. There's two other important limitations. One is that it assumes this discrete time, which isn't really true. This makes it seem like all of the cells reproduce at the same time, and they all die at the same time. Somehow they're all synchronous. There's a synchronous reproduction in the whole population. In reality, that doesn't happen. In reality, one cell reproduces some, and then another cell reproduces a little bit afterwards, but then maybe the first cell reproduces again, and you get more of a continuous process where you're having offspring being produced at all times. Is that clear, the difference between the two? Okay, good. So if we want to somehow figure out how to model this in continuous time, if we want to make it a little bit more realistic, we want to put in finite resources so that we don't get unlimited growth. And there's another thing that we've ignored. All of these cells might not be completely identical. Some, like I mentioned earlier, might produce a few more than another one, and some might produce a few less. Maybe on average they're identical. It's not like this one has a different genome than this one. But there's sort of random variation, and so some of them are going to produce, there's going to be a distribution in the number of offspring. So somehow we have to put a distribution in there. So what I want to go through, basically for the rest of the lecture, is how we add these three sort of complications or constraints into the system, and what that changes about the overall picture. And all the while, I want to be thinking about, what are we doing here? Are we starting from a lower level and building up, or are we doing some of both, starting from a lower level, building up a little bit, and then looking at what we built up and checking that with our experience, and then modifying the lower level to account for that. So think about sort of the process of building this model as I go through. Any questions?
I was wondering, when you talk about the distribution between the different cells,
Yeah.
it's kind of the fact that different cells are going to do different things, and
Yeah.
not all exactly homogeneous.
Right.
How can we also, I don't know if this is even better, think about, like, I don't know, random mutation?
Yeah, so these cells might mutate eventually, right? That's what drives evolution. That's a good point. So I'll just mention this briefly. So remember the Goldenfeld article, he talked about different time scales, and how you can sort of, if you want to understand a phenomenon, you look at the time scale that it takes place on, and you sort of ignore the things that are on vastly different time scales. So evolution, so mutation is an example of this. Mutation and reproduction are on vastly different time scales. Whereas you have a reproduction every generation, let's say, it might take thousands or millions of generations to get a mutation, depending on what's going on below. So because they're on vastly different time scales, we're just going to ignore that for now. If you put some cells in a petri dish in a lab and let them grow for a day or a week, you're not going to really get any mutations. If you let them grow for a month or 2 months or a year, you will, or 20 years if you're at Michigan State. So let's see. Any other questions? That's a good question. The whole Michigan State thing, there's this guy named Rich Linsky who's been doing this evolution experiment for 20 years. It's been literally evolving the same bacteria for 20 years.
Somebody's going to escape.
Yeah, luckily for us, there's a limited resources, so it's all good. Okay, so what I want to do now is I want to deal with the continuous time issue first. So what I want to imagine is that we break the time axis up. So these are like one generation, 2 generation. We break them up into smaller pieces that each have a width delta t. Okay, so this probably reminds you of one from limits of derivatives or something in calculus, and that's basically what we're doing. And I'm going to write down the following. So now we're going to look at the whole population size at t plus delta t instead of at I plus 1. So now we're looking at the change from here to here instead of from here to here. And this is where the whole sum notation is a little bit more useful. So first of all, I'm going to sum over the number of offspring let me just write down first, I'll explain what we're doing. So bi of delta t is the, it's just a number I'm defining, and it's going to be 1 if so 1 if cell I divides in the time delta t, and 0 otherwise. And there's going to be something called di of delta t, which is similar. 1 if cell I dies in delta t, and 0 otherwise. So this is sort of going to keep track of the number of cells. So if we just look at one, if you ignore the sum for a second, let's say that cell I doesn't divide in delta t, but it dies. Then you'll get 1 plus 0 minus 1, and you'll get 0. So there's no cells remaining that are related to that first cell. But maybe what happens is the cell doesn't die, and it divides once, and then you'll get 1 plus 1 minus 0, which will give you 2. You'll still have 2 cells left. So when we sum up this, we're going to get the total number of cells in the population after this time step delta t. Don't worry too much about this. It seems a little bit weird. I'm just sort of motivating how I'm going to do this. Oh, another thing I might say is, what if more than one cell divides? Or what if the cell, what if the cell divides more than once? So you get 3 divisions or something, you get 3 offspring. What we're going to do is we're just going to make the time step small enough so it doesn't happen. We can always do that, because eventually we're going to take the limit of this thing goes to 0. So we're only going to allow 1 cell division per time step, at most. So let me just say, if you just look at a piece of this, man, all of these markers are failing. Can you guys see this? There's a too light. It's hard to see. I'm going to skip a few steps here, but what you'll get if you do this sum is you'll get the following equation. The steps aren't that important, but I want to give you an idea of what the steps might look like. If you're curious about a particular step, ask me afterwards. So we'll get this equation. And now B and D, B is the probability of division, and D is the probability of death. So you can kind of see where I got this from. If I sum over all of the BIs, I'm going to get a 1 every time there's a division, and I'm going to get 0 every time there's not. And so if I sum all those together, I'm going to end up with the probability in the entire population that I get a single cell division. So that's what B delta T is. And D delta T is the probability over the whole population, and I get a cell death. Okay, and then what we can do is now we can rearrange this equation to look like this. for some of you, this is probably very basic. Maybe people aren't familiar with or haven't done calculus in a while, and it seems more complicated. I'm going through the really basic stuff because I want to make sure everybody's on the same page. So this is what we get. If I rearrange that, all I did is algebra. Just move this over to this side and then divide it by delta t. And hopefully everyone remembers that this thing right here is just a derivative when you take the limit. So we end up with a differential equation that looks like this. I'm going to contrast this with the difference equation that we just were looking at. That was like this. Okay, so the top one is the equation we just looked at when you have discrete time. And now, quickly, what I just did, probably too quickly, but we're running out of time, is to derive this equation, which describes the same behavior, but now when time is continuous. So when cells are always dying and dividing, there's not these discrete time steps anymore. And if we just call this, usually it's b minus d is called the rate. It's some sort of rate of reproduction, because it takes into account the number of cell divisions minus the number of deaths. And if we compare these two, they look quite similar. One is some sort of, they both, on the right side at least, have some constant times the previous population size. They're slightly different because this is the, remember, this is the actual number of offspring that each cell produces, whereas this is the probability that they'll produce an offspring.
It could be more than one.
Huh?
It's a rate, not a probability. It could
Well,
be more than one. Huh?
Yeah.
I think it's a probability per unit time.
Yeah, that's exactly right. So it's like a, right, these are probabilities, and this was a probability, and we divided by delta t. So you get a rate. So this is a rate. Whereas this is just a number. Okay. Thank you. Yeah, if I say anything wrong, tell me I'm wrong. Don't hesitate. I hate being told I'm wrong, but I'll take it. 'Cause I don't want to make too many mistakes. So let's say we wanted to solve this now. So now we have another equation we're going to solve, and we're going to, maybe in when you make time continuous, the behavior is very different. Then we'll have to we'll have to decide what do we want to do when we model the system. Do we really want to think about it as discrete time, or do we want to think about it as continuous time? Well, this decision, we'll use whichever one agrees better with the actual experimental results. But just going back to sort of some of the basics, this thing so is called a recursion relation, or in another form sometimes it's called a difference equation. This thing is a differential equation. And in particular, this is a first order linear differential equation. So it's first order because we only have the first derivative here. If I had an equation with a second order derivative as well, it would be a second order equation, so on and so forth. And it's linear because you never have any functions of x or derivatives of x that are nonlinear. So let me give you, just to make that clear, let me give you an example of a nonlinear differential equation. It might look like this. So this is quadratic, it's not linear. And since we have a function of x that's not linear, this is a nonlinear differential equation. There's a big difference between the two, and Oana's going to talk more about that next week. But linear differential equations, we can solve any linear differential. I can solve, or together as a group, we can solve any linear differential equation that you give me exactly in a function I can write down. Nonlinear differential equations, most of them you can't solve analytically. They're hard to solve even on the computer sometimes, and you often get very different behavior. Okay, but we have an easy one to solve. So can someone tell me how I solve this?
Guess. Separation of variables.
Yeah, there's all these different ways. You guys, I'm just going to write the solution. The solution is this. It's an exponential function. And just to contrast that, remember before we got this solution. They look quite similar. Sort of I and time are interchangeable in a sense. And you both have an x0 here. If we want them to be exactly the same equation, then we just have to realize that e to the r, I'm going to put a 1 here, is equal to s. So remember, this is r is the reproduction, the rate of reproduction. So e to the r times 1 is really the number of new cells that are going to be, or the number of cells that you get. I can't unclear. Hold on. It's going to be this. x1, let's say you start with 1 cell, is 1 times e to the r times 1. So it's just the number of cells you'll have in the next time step if you start with 1 cell. And that's exactly what s was. That was our interpretation of s. It was the number of offspring produced by a single cell in the next time step. So far there's no difference. We did this continuous time version, we have this discrete time version. They look slightly different. One has a rate, one doesn't, but the behavior is exactly the same. And just to remind you guys, it's exponential behavior, so it's going to look something like this. The discrete time, all we're going to see are these discrete time points. Continuous time, we're going to see the whole curve, but they lie on top of each other. There's no difference between the two. And this is what we said, it's going to go crazy and go out of control and eventually blow up to infinity. And we don't want that to happen. I guess one other point I should point out is that what happens now for this equation if r is, before we had this regime, if s was bigger than 1, it blew up. If s was smaller than 1, it decayed to 0. What is the sort of transition point between the two? So what, if r is bigger than 1, what happens here? Yeah, what were you going to say?
Oh no, I take it back.
Take it back, okay. So what is r, when r is bigger than 1, what happens to this? Blows up. What about when r is 1/2? Does it still blow up?
No.
Are you sure?
No.
Still blows up. So it's 0 is the point here. So if r is bigger than 0, it's going to blow up. If r is less than 0, it's going to die. And that's consistent with this, because if r is bigger than 0, this is bigger than 1. And if r is less than 0, this is less than 1. So everything's consistent so far. You might think it's always consistent. If you go from difference equations to differential equations, you always get the same behavior. That's not true. And I'll give you an example at the very end when that's not true. And I think Oana will talk more about it next week, but I'm not sure. Okay, so we dealt with, we made our model a little bit more realistic by putting it into continuous time. Now I want to deal with the finite resources. Okay, so this is the differential equation we have. Now let's just think about what actually happens in a population that has limited resources. So the thing has a bunch of cells in there, they start reproducing, and you can sort of think about this as the rate of reproduction of each individual cell. So as the population gets more and more crowded and the amount of resources per cell decreases, what should happen to the rate of reproduction per cell? Decrease, right? So the problem here is this thing's constant in our simple model. And in order to fit the behavior that we actually see, which, just to give you an idea, it looks something like this. So what happens is the thing sort of grows exponentially at the beginning, and eventually it flattens out, and it never gets above, sort of stays constant around a particular value, which I'm going to call K, which is the carrying capacity. It's typically called the carrying capacity. So what we figured out is that R is going to have to be a function of the total population size. and it has to be a decreasing function of x. Now notice what I'm doing. You might think, oh, well, you could probably get all of the, you could figure out what R is based on the microscopic description of the cells. You know, how the cells take in sugar, how they turn that sugar into, how they use that sugar to produce new cells, how the concentration of sugar is affected as the population gets bigger and bigger. There's all of these sort of specific underlying lower level details that should give me this R of x. But I'm not going from the lower level details up to the higher level. I'm going from the higher level observations, and I'm using this simple model to determine what this function must look like. So it's a very different approach than this reductionist approach. So there's a few other things we can say about this. We can say that the rate also has to, when x equals k, the carrying capacity, what does R have to equal in order for us to get a picture that looks something like that? 0. Does everybody see why it's 0? So if R, if it's equal to 0, so I'm going to change this now, there's going to be an x here. If this is equal to 0 when x is equal to k, then the change in the population is going to be 0, and the population is going to stay at the carrying capacity, which is what we observe. So we also know this function has to be 0 when x equals k. And there's a couple of things we can write down about it, but they're not as important as these two. These are the main things about the function. And so our question is, what is this function? So we can sort of draw a picture of what the function might look like. Maybe it looks something like this. I don't know, maybe it looks something like this. Maybe it's a line. There's a whole bunch of possibilities, and based on these observations, we can't distinguish between these. We don't know which ones. So now what we could do is we could now go back to the details of the cells. You know, use a microscope or something and figure out what's going inside of these cells and how the sugar is being distributed to the different cells, and look at all the details and figure out what actually R of x is. But sort of a lesson from modeling is that's complicated to do, that's hard to do. And often we can get an idea of what the behavior is going to look like by just guessing a simple function for R that obeys these. So what I'm going to do is I'm going to guess the simplest function possible, and that's just a line. And so if you think about it for a while, you realize that this has to be, if you want this function to be a line, it has to have this